Okay, so on this next one, these should be easier than the trig function ones. It says in exercises 9 to 50, identify the coordinates of any local and absolute extreme points and inflection points and to graph it. So here's your function for number 9. And so that's the y equal x squared plus minus 4x plus 3. So what we know is our first derivative would be 2x minus 4. And when you do this, factor it, you have a 3, so you got 3 and 1, and the middle term's negative, and this term's positive, so you put minus minus. So let's check it. X squared minus x minus 3x gives you negative 4x, and negative 3 times negative 1 gives you positive 3. So that's the original function factored, and so that means 1 and 3 are the x-intercepts. So then the next one, factor out a 2, and so you get x minus 2, and so that means x equal 2 is a min or max, and when we graph it, it's going to be minimum. So let's do that now. X squared minus 4x plus 3. There's our original graph, and there's the 1 and 3, which we looked at. And then 2x minus 4. There it is. And x equal 2. Notice it's a x-intercept for this one, but it's the minimum in this case. Because on the original it's low. So that's how you know it's the minimum. We can also go to menu, analyze, minimum. Make sure you pick the correct graph and go from here to here. And you get 2, negative 1. So 2, negative 1 is the minimum. So on this one, the graph generally looks like this. This is 2, negative 1, and at 1 and at 3 it had the x-intercepts. And 2, negative 1 we say is the local minimum. So we also need our second derivative, which would just be 2, because you take the coefficient. It's like the slope, basically. So make sure you have your functions, including the factored out part, as well as the graph. And then our descriptions of this are that it's going to rise from 2 to infinity. And it falls on negative infinity to 2. And at x equal 2, there is a minimum. And since y double prime is greater than 0, the curve is concave up for all x. So we got positive 2, and so it's concave up, which is like that. So that's number 9. Our next one is 13. Okay, so our next one is y equal negative 2x cubed plus 6x squared minus 3. That's our original function, and our first derivative would be negative 6x squared plus 12x. Which on that one, you might want to factor out factor out a negative 6x, not just negative 6. And then you'd get negative 6x on the outside and x minus 2 on the inside. So your greatest common factor between these two terms is negative 6x. And so that'll tell you that 0 and 2 would be important. Okay, so I don't mean the ordered pair 0, 2, I just mean 0 and 2. Okay, and then for y double prime, you do your negative 6 times 2 is negative 12x, and then plus 12. So this one, when you factor out a negative 12, you get x minus 1, and so that means x equal 1 is important. So now we're going to graph these. The first one, I've graphed negative 2x cubed plus 6x squared minus 3, and it looks like that. And then the second one, negative 6x squared plus 12x. So that's that one. And then negative 12x plus 12 is just linear with a y-intercept of 12. Remember, that's down 12, right 1, so negative slope. Okay, in general, we're not really going to use the second one. It's getting too crowded. So now we're going to look at the points that we need for this problem. So the first thing we want to do is start drawing our graph. And at 0, negative 3, this is a local minimum. Local minimum. And at 2, 5, this is a local maximum. Now we need to pay attention to x equal 1. So what I'm going to do is I'm going to go to my table, Control T, and at 1 I get 1. So 1, 1 is an inflection point. So basically, that's where it's going to change. And the graph basically went down, and then it went up, concave this way, and then concave that way, down to like that. So based on the graph, you have your description, which is it rises on 0 to 2. It falls on negative infinity to 0 and from the 2 on, so that'd be 2 comma infinity, and at x equals 0 there is a local minimum so that's your local minimum, and at x equal 2 local maximum. And then the next part we need is about the concave up and down. And so this part is when it's concave up. So it's concave up from negative infinity to the 1, and concave down on 1 infinity. And again, x equal 1 is a POI, which is the point of inflection. Okay, so you basically need all of that for 13. For number 17, your function is y equal x to the 4th minus 2x squared. And they went ahead and factored it for you. That wouldn't have been hard to factor. And y prime would be 4x cubed. Again, take your power, bring it in front, and then decrease the power. And then for this one, negative 2 times 2 is negative 4x. Again, going down in power. So that's how I would probably prefer it. If you want to, you could factor it. This is a little more than I would require. Factoring 4x, and you have x plus 1, x minus 1, because it's like 4x times x squared minus 1. So definitely get this part, and of course the original problem. You can see how they got this. They just kind of skipped a step. If you factor out your 4x, which is your greatest common factor, then you're left with x squared minus 1, and so then that would help you understand the factoring. So that would mean 0, x equal negative 1, and x equal 1 are important to look at. And on this one, x equals 0, and then the other part, if x squared is 2, x is square root of 2, both on the positive and negative end, would be interesting. Okay, the next part we need is for the second derivative. So 4 times 3 would be 12, 12x squared minus 4. And for this one, of course, we factor out a 4, we get 3x squared minus 1. So for this one, 3x squared minus 1 equals 0, 3x squared equal 1, x squared is 1/3, so x is plus and minus the square root of 1/3, which in the book, they're taking the square root of 1, because that's easy, and then putting square root of 3 on bottom. You don't have to rationalize the denominator. They're leaving that to be optional. So those are the points we're going to be interested in. So our next step would be to graph it. X to the fourth power minus 2x squared. There's the graph. Let's analyze, get the minimum from here to here. We got -1 as a minimum. And 0, 0 is the local max. And it's symmetric, so 1, 1 is the local min. One -1 right there. And so that's the curve. Now between here was that inflection point, which we're using this value. So 1 over square root of 3 is approximately 0.577. Okay, so at this point, all I have is my local minimums and maximums. So now I need to graph my derivative function, 4x up arrow 3 minus 4x. So you can see right there it coincides with that. That's why it's so useful to get your derivative if possible. And on these polynomial functions you can. And then the other one, 12x squared minus 4, that one's going to help you know your point of inflection. So these are going to be from the point of inflection. And when we plug in that to the original, let's go to the table settings. I'm going to do independent to ask. And 1 over square root of 3. On my calculator it converted it, but anyway, you get -0.5 repeat. Remember, you can copy that, Control C. It's -0.5 repeating, and you can paste it, Control V. Now the 7 won't really do us any good. It's probably like a calculator error right there, because if you round you really should have gotten 6 there. So I'm just going to delete that guy and go convert to fraction. Whoops, I meant to decimal. Wait, really? Let me put in some more 5s. when it's the same number repeating, it should be divided by 9. Okay, so I just needed a couple of extra, and there you can see the 6. So that's ending up with a negative 5/9. So we have negative 1 over square root of 3. I'm just going to say plus and minus to help y'all out, with negative 5/9. That's your point of inflection. So like halfway between, and then going down, and then like this, and then up. So I think we did okay on labeling it this way. So now your description is it rises on from negative 1 to 0 and 1 to infinity, and it falls on negative infinity to negative 1, so basically anywhere to this point, and from 0 to 1. So that's about the rising and falling. And then at x equal plus and minus 1, there are local minima. So those are the two local mins. So they say minima, not minimums. And then at x equals 0, a local max. And then using what we did just a few moments ago, concave up on negative infinity, negative 1 over square root of 3, and this other part, 1 over square root of 3 infinity, and this is concave down in between there. And as we already wrote, the points of inflection are there. So that's number 17. Our next one is number 21. Same instructions, and on this one you have y equal x to the 5th minus 5x to the 4th, and they already factored that out. Factor out your greatest common factor, and it's x minus 5. So what that means is that at x equals 0 and x equal 5, that's going to be important to us, basically from the factoring. The factoring really does help. If you're good at factoring, you might be able to do the problems quicker. And then do your derivative. You get 5x to the 4th minus 20x cubed. Again, negative 5 times 4 is negative 20. Now on this one, again, they want you to factor it out to speed you up. And you got a 5 and an x cubed that we can factor out. So you get x minus 4. So this one means x equals 0 and x equals 4 are going to be important. And then the next part is the y double prime. So this would be 20x cubed minus 60x squared. So on that, when you factor that out, you could say 20x squared, basically 20x squared and you have x minus 3. So that means x equals 0 and x equals 3 are important. Okay, so there's all your information, and we're going to want to graph this. We are going to have to change our window quite a bit. Let's graph this. X to the 5th minus 5x to the 4th. Before I type any other functions in, I'm going to go ahead and change my window. Just choosing a large number. It's too big. But let's try it again. Whoops, I left off a 0. It's okay to make a mistake. Okay, so there we go. We just learned from our mistakes. And analyze minimum from here to here. 4 comma negative 256. Is a local minimum. And 0, 0 was a local maximum. I'm making a very large scale factor. It's counting by hundreds. Okay, and 4 is negative 256. So more than halfway there. So of course this is our min and that's our max. The other thing we're going to need is the 3, which is our point of inflection. And that ordered pair would give you 3 comma negative 162. So it's not exactly half because it's not a trig function. What you do is you plug in your 3 here or use your table like we did before, and that's going to be your point of inflection. So at that point it's going to go up, and all this other stuff is going to come together pretty nicely. That's where it changes. So this is your point of inflection. This is your minimum and your maximum. So rises from negative infinity to 0, and it's rises, and 4 to infinity, and it falls on 0, 4, and there's a local max at x equals 0, a local min at x equals 4, and it's concave down on negative infinity 3. So that's where it's down, and it's concave up on 3 infinity. And as we said already, x equal 3 is your point of interest, or point of inflection. Okay, that's going to be good for this video. Hope y'all are having a good day.